So that brings us to the second law of thermodynamics. You might recall the first law of thermodynamics, and that was basically the conservation of energy. And we had this equation where we have internal energy. So we have internal energy, and this is heat flow, and this is work. So the change in internal energy is due to an exchange. So if you have the system, and it is gaining or losing internal energy, it does so by exchanging energy with the surroundings by either heat or work. So this is about quantity of energy. And when we talk about enthalpy, delta H, remember enthalpy is a defined function in thermodynamics. So the internal energy of the system is a combination of kinetic energies of the particles moving around. There are rotational energies also, but also the stored potential energy and chemical bonds in the sample. So that's what the internal energy is. And the enthalpy is similar to that. We make this definition of enthalpy that's related to internal energy, but it allows us to ignore the work component. When you work under constant pressure, when you're doing work, I'm sorry, I shouldn't say work, but when you're doing, say, a chemical reaction or some process under constant pressure, then the heat flow is going to be equal to the enthalpy. Now, could there be work done? Yes, there could be work done, but we ignore it as chemists. We just consider the heat. You can usually calculate the work if you need to. It's usually for chemical reaction, the formation of a gas or a gas is consumed in the reaction, and that either pushes against the atmosphere surrounding it, or the atmosphere is able to push in as gas is consumed. And so that is the work component. And we can calculate that part through the ideal gas law, basically. But we're usually just interested in measuring the heat, and we relate that to enthalpy. If you do things under constant volume, which is a whole different type of experiment, then the heat you measure is not enthalpy, it's the change in internal energy. Hopefully you remember that. So the first law is all about the quantity of energy, that it's conserved, it's exchanged by work and or heat. The second law of thermodynamics is what we're talking about now, and that's the dispersal of energy. So during a physical or chemical change, some energy is dispersed. So we think of energy as being concentrated or dispersed. And whenever we have a change, some energy gets dispersed, less concentrated. So that's the second law. And so the diffuse disorganized form of energy increases, the concentrated organized form decreases. So this is about the quality of energy. Okay, this is about the quality. And what do I mean by that? Well, if you need some energy source to do something, you're looking for a concentrated organized form of energy that you can extract. In doing so, you will disperse some of that energy, and and some of it will be dispersed, and you don't get use out of it, actually. So the quality of energy, whether it's concentrated and usable or more diffuse and unusable, is what this law is about. So the thermodynamic value that we use is entropy. So we have enthalpy, which is related to the heat flow, and well, basically it's related to the internal energy. But the entropy is a measure of dissipated energy at a given temperature. So if you increase entropy, that means you are dispersing energy. Now, what is entropy then? Let's talk about it some more. So it's a measure of the dispersal of energy in a system out of the different possible ways the system can contain the energy. So sometimes you can think of this as a measurement of randomness or disorder, because if you can organize energy into a highly ordered state, versus, that's what entropy is a measure of, how organized or disorganized the energy is. And that energy organization could be, energy held by the particles themselves, like their kinetic energy, motion, also the organization of the matter itself. So in a way, when you look at the sample, say, of a gas, every particle has some kinetic energy and is moving around. And so when you push all of the molecules close together, you're sort of concentrating and organizing that energy, as opposed to it being spread out over a larger volume. And remember, entropy is increasing when disorder increases. So concentrated forms of energy and matter is low entropy. Moving to more diffuse energy, more disorder, more randomness, that is high entropy. Now, the first thing you might notice is that the units are joules over Kelvin, or if it's on a per mole basis, joules over k mole. Joules are a unit of energy, and so that's joules, which is energy, over Kelvin, which is temperature. And remember, it's a measure of the dissipated energy at a given temperature. So when entropy increases and energy is dispersed, you could calculate the amount of energy that's dispersed. But the entropy isn't just simply the energy, it's that amount of energy at a given temperature. And so you can see from the units, you take the energy and you divide by Kelvin. And another thing you might recall is something like enthalpy or delta E units. They were usually kilojoules per mole, or just kilojoules, but if you're doing it on a per mole basis, then kilojoules per mole. So not only is entropy a little different because we have the energy divided by the temperature, you also notice that it's kilojoules versus joules. So the numbers are usually a lot bigger for enthalpy and internal energy in terms of kilojoules, or in terms of joules per mole. So instead of saying 30,000 joules, we say 30 kilojoules. But the numbers for entropy, joules per Kelvin, are smaller numbers, so we don't convert it to kilojoules. Now, remember, greater disorder equals greater entropy. Greater order means less entropy. So we have two possibilities being compared here, that the change in entropy for the system is positive. So it's positive. So what does that mean? The final state is greater than the initial state. So the final state has higher entropy. That means it has more disorder. Energy is dispersed. So energy is dispersed. Now, if delta S for the system is negative, then the final state is has less entropy than the initial. So that means the final state, if it has lower entropy, it has more order, less disorder. So we've increased order, or energy is concentrated. So spontaneous changes always occur such that the total entropy increases. So does that mean that delta S is always positive? You have to be careful. The total entropy refers to everything. The entropy of the system and the surroundings. So this refers to the entropy of the system plus the surroundings. So if you have an isolated system, no exchange of matter or energy with the surroundings, there's no change in entropy. So delta S for the surroundings equals 0. There's no exchange, right? So if the only change in entropy for the system is that of the system, then it must be positive, because for spontaneous changes. So if it's an isolated system, then delta S must be positive, and entropy will never decrease for spontaneous changes. It has to be greater than 0. Now, continuing with this thought, if we instead consider non-isolated systems, this idea that the total entropy increases, that refers to the universe. So this must be positive for spontaneous. Now, you can have the system change in entropy could be positive or negative. But the sum of these but the sum of these must be positive for a spontaneous process. Okay, so you can have the change in the entropy of the system be negative if for a spontaneous process, if the change in entropy of the surroundings is negative enough to make the total change. I'm sorry, if the delta S of the surroundings is positive enough to make the total entropy change positive. Now, can you have a non-spontaneous process? Yes. So what do we mean by that? The system change in entropy can be negative, and that would be a non-spontaneous process in reference to the system. But for that to be occurring, you need to have delta S for the surroundings be positive to counter that. So just a couple more ways you can consider entropy. One is that you will find it completely impossible to completely turn heat into work. You know, the study of thermodynamics is tied in with the development of motors and engines and efficiency. And what are we doing with these engines? We're taking heat from a source, from steam, or later from, like, say, the combustion of gasoline, and we're transforming it into work. So by generating heat, we transform that into work. You would like to transform as much of that heat into work as you possibly can. That would give you the best efficiency. However, it is impossible to do that 100%, because whenever you have a change, some heat or some energy is dispersed. Okay, so some energy is going to be dispersed when you try to do this. Not all of it is going to be converted into work. So if you could completely turn heat into work with none lost, that means you would completely convert diffuse energy into concentrated energy. Yes. So by doing work, that's another way of saying you'd be concentrating the energy to perform work, and you must lose some of the heat to the surroundings. It cannot all be put into work or concentrating energy. Also, when converting thermal energy into work, some energy is lost as heat to a body of lower temperature. It's just another way of saying that. So it's just another, as I said, another way of saying that. And then heat, I mentioned this before, heat flows from hot to cold bodies. I should be more careful there. Or, yeah, I'll just leave it at that. So this disperses energy. So if you put, if you have water at 25 degrees C, and then you drop in, let me say, a piece of copper at 200 degrees C, heat is going to flow from the hot copper into the cold water because that is dispersing the energy, not concentrating it. If you were to concentrate it, that means the water would get colder as heat flowed into the hotter body. So that wouldn't make any sense.